I am Olivier Grasset. I am a researcher in planetary sciences, mostly involved in the exploration of the icy moons of the outer solar system. Right now, I am also vice rector in charge of research for the Nantes University. But regarding GEOS, I have been involved for almost 12 years now. That means right from the beginning of the story, which was at that time the Laplace mission. And recently, I've like two colleagues involved as an interdisciplinary scientist in the project. To be an interdisciplinary scientist means a lot to me, because it means that once again, I am involved, as a scientist who has in charge the good interaction of the different communities in order to make the mission a great success. This is the way I see it. There is a huge diversity of planetary bodies while we are in the same planetary system. Io is a small moon with no ice, extremely dynamic. Europa is like Io, but you put an hydrosphere of 100 kilometers thick, and in which there is a liquid ocean, as far as we know, and in which the exobiological potential is huge. As far as we know, the icy surface is a few tens of thousands years old, no more. So that means that it has been recycled many times, and it means that the moon by itself is very active due to the gravitational interaction with other moons, and especially with Jupiter. Then you go further away, and you have Ganymede, the biggest object in the giant system. The moon is slightly larger than the Mercury planet, in which, compared to Europa, you simply add more ice, more and more hydrosphere, meaning that you have, an iron core, a thick silicate mantle, above which you put a huge hydrosphere, which is made of few hundreds of kilometers of ice plus probably liquid water too. Ganymede is much less active, but still active as far as we know. But the activity is in the interior, because as far as we can see, the surface itself is a few hundreds of million years old. The youngest surface, because there is also old surfaces which are billions of years old. And then you go to Callisto, and there the body has been in it for possibly billions of years. From what we can see, there has been no activity at all, which has been registered on the surface of the moon. When you get the big picture, you have the big panel of 4 moons, which are so extremely different in terms of composition, history, exobiological potential, geological activity, and so on and so on.
My name is Luciano Yes. I'm a professor of space engineering here at Sapienza University of Rome, and I'm the principal investigator of 3GM, which stands for Gravity and Geodesy of Jupiter and the Galilean moons. 3GM is actually an assembly of 2 instruments provided, one by the Italian Space Agency, funded by the Italian Space Agency, the other one from the Israeli Space Agency. And the second instrument, which is an ultra-stable oscillator, will be used to probe the atmosphere of Jupiter, and as well as the ionospheres of the moons. The second part of 3GM is an instrument called K-band transponder, which allows very precise measurements of the velocity of the spacecraft. We can go down to precisions of the order of a few microns per second, if you think. And it's always astonishing to understand how we can do such accurate measurement at such large distances. It's electronic engineers working at the station and with transponders are doing an excellent work. How are we using these precise measurements? Because by measuring how Jews will fall into the gravity field of Ganymede and the other moons, will provide essential clues to the interior structure of those moons. So ultimately, 3GM, together with other instruments, onboard instruments, especially the laser altimeter GALA, and the magnetometer, will be able to do a tomography of the moon. So we will peek through the surface and give a sort of X-raying, a tomography of Ganymede especially, and the other moon to a lesser degree of accuracy.
My name is Hauke Hussmann. I'm the principal investigator of the GALA instrument, the GAnymede Laser Altimeter, one of the instruments on board JUICE, of course, and I'm located at the Institute of Planetary Research at DLR in Germany, in Berlin. GALA is a laser altimeter, and it fires laser pulses, short pulses, 30 times a second to the surface of Ganymede, and also during flybys to Europa and Callisto. And these pulses are then reflected at the surfaces of the icy moons and reflected back to the instrument. And a very sensitive detector is recording the return signal. And this gives us information, first of all, on the range that we have from the instrument to the surface. And if we know the position of the spacecraft and the orientation, we can then have a 3D topography of Ganymede and the other moons along the track. And combining many tracks, we then have a 3D information on the entire surface globally on Ganymede. The other second major objective is the tidal deformation of Ganymede. So we are in orbit around Ganymede for 130 days roughly. And this gives us the opportunity to measure the tidal deformation as Ganymede revolves around Jupiter. We will have a tidal elevation, so the surface is moving. And this can be recorded with a laser altimeter. And the question, of course, is why do we do that? And here the objective is to get evidence for the subsurface ocean on Ganymede. So the tidal signal is indicative of whether there's an ocean there inside Ganymede, a water ocean, or not. In case of an ocean, the tidal amplitudes will be several meters, so that will be detectable with GALA. And if there's no ocean on Ganymede, the tidal amplitudes will be only a few tenths of centimeter at maximum. So this is the big difference between these two cases, and therefore we are sensitive to detect the ocean, and in conjunction with other instruments to determine its characteristics, ice thickness, ocean thickness, and some other physical properties.
My name is Lorenzo Bruzzone. I am professor at the University of Trento in Italy, where I am the coordinator of the remote sensing laboratory. I work on remote sensing and radar stuff for planetary exploration and Earth observation. And in the JUICE mission, I am the principal investigator of RIME, which is the radar for Icy Moons Exploration, which is a radar supported by Italian Space Agency with the collaboration of NASA. RIME is a radar that works at a very low frequency, and so this radar transmits electromagnetic wave toward the surface of the icy moons of Ganymede, Europa, and Callisto, and part of this wave propagates into the subsurface. So what we would like to do is to study the subsurface up to 9 kilometers of depth, because with the radar we have that every discontinuity that we have in the subsurface that can be mechanical, dielectrical, thermal, generate an echo. So we are in the condition to measure this echo and to construct images that represent the profile of the subsurface. So we will get information that will help to understand what is the subsurface world of the icy moons. And these are direct measurements that will allow us to profile the ice shell that we have in the 3 icy moons, to study the features that we have in the subsurface, to analyze the correlation between the features that we see in the surface and what we have in the subsurface, to study the process of evolution, the tectonics, the impacts, the cryovolcanism, many different interesting targets. And of course, a radar like this has the capability to detect the possible presence of water. So we are in the condition in which if a pocket of water is close to the surface, we can measure that. And we may be in the condition in Europa to see the interface between the ice and the possible ocean. And that, of course, is a quite important science objective that we have.
If you look closely, it's a 1:18 scale mock-up of the JUICE spacecraft. What you see is the key features. The spacecraft have all kinds of little protrusions, antennae, probes, etc. And what we're doing here basically is, if you look very carefully, you see the RIME antenna. We are in this huge anechoic chamber, which is designed for normal antennas, and these cones basically filter out what's from outside, but also what goes outside. RIME is in reality very big, it's 16 meters. That generates a 9 megahertz signal. But we cannot measure that here. It would just go through the facility and we couldn't measure it. So by scaling JUICE by 18 times, so 18 times smaller, physics helps us by making the frequency 18 times larger. And this we can measure here. We have a very representative model, at least from a radio frequency point of view. And what we are basically doing here is we are measuring how the antenna functions with all the interference from the surrounding structure of the spacecraft, and by changing the angles of the solar rays. And now, when we leave and the door closes, the instrument will be continued at a certain angle. The measurement is done of basically the pattern, the antenna pattern, and this is then compared to the model. And at the end we will know if our model is good enough to predict how the RIME antenna will work. And that's the only way on Earth that we can actually do this. We've tried with a helicopter to also do a similar test. However, with the helicopter we could only do one aspect, but because it's moving and oscillating underneath the helicopter, it's not good enough for all aspects. So this is an add-on to really see the static behavior of the dipole on JUICE.
This is a technology that has been tested. It has been used on the Moon. It has been used on Mars with a couple of systems. So it's something that has been tested on planets that are close to our Earth. But this is the first time we go on the outer part of the solar system with an instrument like this.
My name is Leonid Gurvits. I am principal investigator of one of the JUICE experiments, and it is with my pride to represent PRIDE. This is a combination of radio astronomy instrumentation and telescopes located all over the surface of Earth, and by means of using this network of radio telescopes, we will support certain science activities, science applications of JUICE mission. PRIDE experiment will employ the instrumentation developed for a technique called very long baseline interferometry. It's a technique which combines many radio telescopes in such a way that together they work as a single system, and there is a fundamental law of physics. Angular resolution, sharpness of vision, is proportional to the wavelength at which observation is made and inversely proportional to the size of the telescope. So we synthesize a huge telescope which basically comparable in its size to the diameter of our planet.
Prenez le rond-point, puis prenez la première sortie.
Everybody nowadays knows about navigators which we use in our cars or even with a bike or even just walking. So typical precision is something like 10 meters, right? That's enough. Well, our technique is such that if you are lost anywhere in solar system, no problem, give us a call. We'll find you with a precision typical by TomTom or Garmin, whatever navigator you use. Our measurements deal with lateral position of spacecraft in the sky, but also in the name of our experiment there is letter D, which stands for Doppler. Whether we want or not, but the mechanism of our measurements is such that we measure radial velocity of spacecraft by means of detecting Doppler shift of the frequency of transmission radio signal from spacecraft. And in this domain, we are also quite precise. To give you some sense, we can measure radial velocity of spacecraft with a residual noise, with an error, measured around 10 micrometers per second. Micrometers per second. Well, imagine what is the precision of Doppler measurements when we get tickets for speeding. I don't know exactly, but tens of meters maybe per second. But we measure micrometers per second. Still, it's possible. And combination of these data and lateral position and of course other measurements by other experiments of Jews, all together that will provide input into studies of interior of moons. It provides the means of investigation of Jupiter, and of course that will be a very useful benchmark for studies in the area of exoplanets. As history of science teaches us, and certainly that is the case of radio astronomy, it is practically impossible to predict main discoveries. When you build a new experimental system, whether this is telescope like that, or a new mission which will go to Jupiter, or anything else, certainly to convince funding agencies and governments, you have to present a list. Well, we'll discover this. And in most cases, we do that. But it turns out that the most interesting thing is the one not predicted. And you can find it everywhere. By improving a little bit this, a little bit that, yeah, that's good. But that's good for your home appliance. But when you do some really front-edge science, you have to make a big jump. In this sense, in my opinion, and again I repeat, I'm not a planetary scientist, but my understanding of the essence of JUICE is such that it does possess this characteristic. It can do certain things significantly better than anything else. I'm sure that major discoveries will be in this, something provided by that. What specifically? We'll see.